Oh, howdy kids, this is Mr. Dawkin. Today we're going to talk about some VSEPR shapes, and today you need to know what VSEPR means. VSEPR stands for valence shell electron pair repulsion theory. This is not some boomerang you can just loop around and have it come right back to you. You gotta study it, you gotta know it, and here we go. Okay, this is Dawkin for real because I can't keep the video going that long with Australian accent. So we're going to talk about shapes today. Go back to your geometry class and let's talk about shapes. So we got some magnets down here in the bottom left, and the magnets, they will repel if they have the same pole next to each other. And because electrons are negative, they are going to repel each other to be as far away as possible. Kind of like me and Mr. Cantu. We have opposite rooms, and sometimes we just try to get as far away from each other as possible. But when we have opposites, they attract. So when we're talking about covalent bonds, the electrons are going to want to be as far away as, from each other as possible because they're both negatively charged. So I'm going to refer to these things called REDs in this video. REDs stands for regions of electron density. And so for short, sometimes we abbreviate it as RED. And a region of electron density can be several things. You may want to write this down. It can be a single bond. It can be a double bond. It can be a triple bond, and it can also be a lone pair. And so what we're going to do is walk through some molecules. We're going to count up the REDs, and because those are where we find electrons, those are going to be as far away from each other as possible, and we're going to see what kind of geometry that leaves us with. We call that VSEPR. So here is the molecule for CO2. It has two double bonds, and it has lone pairs outside on the oxygens. So when we're talking about REDs, we're going to look at the REDs, the regions of density, around the central atom, the center atom. So we have two regions of electron density around the carbon atom. We have two double bonds that are pointing out from each side of the carbon. And because these regions want to be as far apart as possible, I'm going to go ahead and draw in the REDs, the regions of density, and you'll see if they were balloons, they would be as far apart from each other as possible. And so we call this shape linear. This is shape number 1 for molecular geometry. And I think I have another picture here, kind of a cartoon image. You'll see that they are far away from each other. Now, it wouldn't make sense if I drew it like this, because then there's tension here. And they don't want to be there. They want to spread out. Okay, next one, carbonate. And remember, carbonate had resonance. The double bond can be in two other places. In this Lewis dot structure, there are 3 regions of electron densities, 3 REDs. And I'm going to go ahead and draw those here. And remember, we're looking at the center atom only. I see 3. We have a shape for this. 3 REDs, we call it trigonal planar. Trigonal planar. Some people call it triangular planar. They want to be as far apart as possible, and you'll see the triangle shape. So we can kind of see how this makes a triangle. Once again, it wouldn't make sense if I had all 3 in the same area. There would be tension there, which we don't like. CH4, this is called methane. We have 4 carbon to hydrogen bonds. There's 4 electron pairs, 1, 2, 3, 4, which once again we call REDs. So if I were to circle those for you here, and we have a shape for this. On a 2-dimensional screen, it looks like the bond angles, the space between the bonds, are 90 degrees. But when they arrange themselves in 3-dimensional space, there's a little bit more room, and they can spread out even further into what we call tetrahedral, which is the 4th shape in our notes. Tetrahedral molecules have a bond angle of 109.5. It gets to spread out just a little bit more. NH3, here's the dot structure. Something's changing on this one. We have 3 bonds, but you'll notice that there's a lone pair of electrons on the center atom of nitrogen. So we don't just have 3 reds, 1, 2, 3. We have 3 reds plus another red, which we call a lone pair. So technically there are 4 reds in this picture. 1, 2, 3, 4. One of them's a lone pair, and so we have a specific name for this shape too. This shape is called trigonal pyramidal. Trigonal pyramidal. Some people call it triangular pyramidal. The lone pair takes what would have been a trigonal planar shape and it bends it down into a pyramid. A triangular pyramid, to be specific. Water. This is going to be our last type of shape, and then we'll do a few more practice problems. Water, we've drawn before in our notes, has 2 bonds, and we'll have 2 lone pairs. So there's 4 reds, 2 of which are lone pairs. And so we have our final shape called bent. Super fancy name. Some people call this the Mickey Mouse orientation because it looks like it has Mickey Mouse ears when those lone pairs are on top. So what would be a linear shape, the lone pairs that get thrown on there bend the shape down. And that's how we get a bent shape. I'm going to go ahead and stop here and create another video for the rest of the examples. Continue on if you need to fill in the rest of your examples.